Hello and welcome to this module 9. So here we're going to see our second optimization techniques for FSM. In this case, we are going to see about state assignment. So earlier we have been using symbols like S0, S1, S2, S3 and so on to name the states, and we have been arbitrarily assigning codes for it. And in this module we're going to see some specific methodologies so that it can result in better design. So here is a simple example. So basically state assignment or encoding is assigning of codes to the state of an FSM or your state transition graph or your next state table. So here you can see in this particular example a pattern detector which detects these two patterns 0110 and 1010, and this is your state transition graph that is given here. So here you can see that we have 7 states. So we could arbitrarily assign some codes. So here, as you can see, we can assign state A as 000, B as 001, C as 010, and so on. And then we actually see what our design would yield. And so here you can see that our design requires, because it has 7 states, it requires 3 flip-flops and 13 gates. So if we actually assign something different, so here you can see our second assignment is shown here, then you can see that again, because it still has the 7 states, we will still need 3 flip-flops, but the total number of gates to implement our FSM becomes only 5. And also apart from the number of gates, you can also consider the number of inputs to each gate, and you can also see that this will require more number of input to the gates, and this less number of inputs to the gates. So how do we go about assigning these states to our assigning these codes to our states? So here is again a simple state transition graph that is given, and so we can see there are 2 assignments that are possible. So here is one assignment and this is our second assignment. So in this case we are going to assign like S0 is 000, which is this is going to be 000, and since from this state you can go to this state or this state, so it is recommended that you actually assign states S1 and S2 one Hamming distance from S0. So that's basically the fundamental principle of the bit change method. So here, as you can see, from S0 we go to S1, but the number of bit changes is 2, and then similarly we also go from S0 to S2 and the number of bit change is 3, and then from S2 to S3 you can see again that is 2 bit changes. So there's a lot of bit changes in this assignment. So we can also do what is called as a state map, and this is nothing but a K map, but except that instead of actually putting in zeros and ones in your K map, we are going to just put what the state is basically going to take a value. So here you can see the state S0 is taking a value which is 000. So, and then similarly S1 is actually taking a value which is going to be 101, and so on. So but in this case, if I have to go from this state which is S1, so you can see that I have to have 2 jumps in there, and then similarly from S0 to S2 I have to go 1, 2 and 3 jumps there. Then S2 to S3 I have to do 2 jumps. S1 to S3 I have to do 1, 2 and 3 jumps. S3 S3 to S4 is good, just one jump, and S4 to S1 is going to be two jumps. So the total number of jumps that are going to be for the first case is about 13. So, and then if I actually try to optimize or do a better placement, so I know that I have S1 and I need I have S0 and S1 and S2 are the next states of S0. So you can see that I've placed them in one jump, and then similarly one jump from S0. So you could also do S2 there. So that's another option. So, but this is one of the solutions. So you have S2, and then from S2 to S3 is only one jump. S1 to S3 is only one jump. S3 to S4, which is here, I put it here, is one jump. And then again, once I've put that, then I have S4 to S1, that'll become two jumps. So the total number of jumps in this case is only 7. So now if I try to implement the second solution, so you're going to see that we're going to have fewer number of gates, and we are also going to have fewer number of inputs to those gates. Obviously, we will not have a reduction in the flip-flops. The reduction in the flip-flops comes from state minimization, which we saw in the last module. So here is another example. So this is our example that is given. So we assume that we've already reduced the number of states in this case. So this is your reduced next state table, which is reduced. And once we have this, so here you can see there is one assignment which is given. So we can, it is easier to actually look at the state transition graph and figure it out. So we draw the state transition graph for that particular problem. And now we can see that we have A to C. They can go to each other. So therefore, they will be actually 2 times the number of jumps because you have 2 arrows in it. So therefore, here you can see we have A and we want to put C as close to each other. So that'll be 1 jump, but you have 2 instances of that. Then we have C to F. So C is there, so F is there. So we have actually put 1 jump for them, and you have only 1 arrow. And then E to F, as you can see, this one, E to F. Now, unfortunately, you have 2 of them, and they have 2 jumps each because you have to go through this. So therefore, there is 2 times 2. Then E and B, they're close to each other. There's only 1 arrow, E and B. And then we have B and F. So here again, B and F is 1 times 1. And then we have B and D, which is close to each other. So we can have 2 times 1 again for the 2 arrows, and then we have 1. So when we actually add these things up, you can see that we actually have 11 jumps or 11 as your bit changes, 11 bit changes for the code assignments. And now we have another scenario where you can see that we have a C as shown here, which is going to be 2 times 1. And then we have this one, C and F. So C and F was also close to each other, 1 count. Then we have F and E. So F and E actually goes 1, 2, and 3. So you have 3 of them. And so that's a 6 on that case. Then you have BF. So BF is again 1 times 2 jumps. And then we have BD, which is 2 times 1. So this one will actually give you 13 having distance for the codes. So therefore, we have these 2 solutions. So you can actually implement this. And here is a solution that is given for the 13-bit change. So these are your assignments, so wherever you actually place them. So here you can see we have 0, 0, and 1 for your A. So therefore, in terms of Q1, So that will be actually the reverse order will be 1 0 0, which is Q3 Q2, sorry, Q will be Q1 Q2 and Q3. So this will stand for A, and so on and so forth. So if we implement the D flip-flop for that particular problem using D flip-flop, so here you can see these are your input equations to your flip-flop. This is your output equation, and over here if you're required to calculate in terms of gates or gate inputs or in terms of transistors, so you can do so. So here you have a 3-input AND gate and then a 2-input AND gate, and these two are connected by a 2-input OR gate. This one doesn't have any gate. Similarly, a 3-input AND gate followed by a 2-input AND gate, and then linked together by another 2-input OR gate. So in total we have basically the number of gates in so far we have is 1 2 3 4 5 6, and then again over here you can see that we have 3-input AND gate, 3-input AND gate, 3-input AND gate, which is that 1 1 1, and then we have a 3-input OR gate, which is that. So this effectively gives you 10 gates, and then if you want to count the number of inputs, it's 3 plus 2 plus 2 plus 3 plus 2 plus 2 plus 3 plus 3 plus 3 and plus 3, which will give you 26 of them. And now if you want to actually create in terms of transistors, so here is a table. Usually the NAND will actually give you the smallest, or the NOR, and you will need actually to use an inverter to get the AND, which is the 2 more transistors. So you can actually take AND 3, look this up, so then you can put 8 transistors for this case. R2 is 6 transistors for this case, and you have AND 2, which is 6 transistors for this case. So you can actually add up these transistor values for all one of these gates, and then end up in terms of transistor count. And here is your kind of expressions that we actually, or the K-maps from which the expressions that we calculate. So the next one we see is called one-hot encoding. So we will actually see this one-hot encoding in our next part of the module.